Okay, so hello everyone, and welcome to the fifth day of our workshop. This is the last day, and the last series of quizzes and one assignment will be made available later today. Okay, so Alex, since we're ready, I will just make you a host and you can start.
All right. I'm on a different setup today since I'm abroad, so things might look a little bit different. So this is the notebook we'll be working on. Just one more moment. All right, here we go. So as I was saying yesterday, today we'll do some graph theory. I will introduce what graphs are and our problem, and then we'll be working with something we do know, which is Grover's algorithm, and we'll try to design oracle or oracles for different versions of the problem. So we can start easy, which is what is a graph? A graph you can write as a collection. So this would be a graph, this pair. Of vertices and edges. As you can see here, 0, 1, 2, and 3 are vertices, while the lines connecting them are edges. And that's all a graph is. Now, graphs have many interesting properties which have been explored in depth, but we will be looking at one of them, which is the problem of a max cut. But first, we need to introduce some more things. So we have this graph, and we have two colors, red and blue. And we want to color the vertices in a very specific way. And here the edges will matter. Meaning, first we'll take red, and we'll color any one of the vertices. Red and blue don't really matter which one you use, but it matters that there are two distinct colors. Then we're looking at a connection at an edge and coloring it with a different color, which would be blue in that case. Next, we have a rule. If we connect two colors, what we would like to do is we don't want two don't want an edge where two vertices which this edge connects have the same color. So in this case, what we can do is we can color this blue since there is no line, but here we cannot do anything else really because here we'll go to this edge. Okay, we need to color it red, but here we already have red. In this example, we have this coloring we had here. But now we can see how many edges there are that are connecting vertices that are colored using different colors. So here let's use green for marking them. So here we have 0 and 2, and they have different colors. So this counts. And 2 and 3 also know they have different colors. And all the other ones, the pairs have color red. meaning they do not count in our, well, let's say game. Next, this example, which I drew here, we can see how many there are here. So here, this one will count, this one will count, this one will count, and this one will count. This connects two red ones, so it doesn't count. And as you can imagine, we want to maximize the number of the green edges. That's our problem. So there are algorithms which actually explore the coloring, and there are greedy algorithms which do it. And why presented an algorithm that is a bit greedy in that way? Do we have to use only two colors? Yes, in the problem that is, well, the key coloring problem, which is more popular, I'd say, than the max cutting problem. Yes, it matters that we use as few colors as possible. So in this case, for example, if we were talking about that problem, we have to color it a different color, and our maximum number would be 3. And in that problem, we would want to minimize it. But the problem we are exploring, for now, we have only 2 colors. I'll explain why in a second when we see the definition. So I'll just write it down as a different sort of problem, which is very interesting, which is the K-coloring problem. And it was a greedy algorithm. It's on the side. But here we only have 2 colors, so the rules of the game are we have 2 colors. So we'll create 2 sets. Next, we're coloring the graph in some way. And finally counting edges, let's say connecting 2 colors. So we come to the definition. So the problem that we're looking at, maybe I'll make it a bit bigger. It's visible. So we're finding the maximum number of edges so that their endpoints are colored using different colors. And this is one of the definition of the max cut problem, which we'll be talking about today. There's another definition where we're saying that we want to partition the vertices of the graph into 2 disjoint sets, and this is called a cut, such that the number of edges between the 2 sets is maximal. Let me explain. And this is the more common definition. We have 2 sets. One is red, and the second is blue. And we have some graphs. So I will mark it as red and blue here. So all these vertices will be blue. And all these ones will be red. And here, we'll have some edges in between them. So what we have here is the green edges, which we're talking about, will be only edges connecting the group of reds with connecting the group of blues. So all of these ones will be the green edges. There can be some edges in between the blue ones and the red ones, but we don't really care about those. So we want to maximize this number. So the green edges. Through a proper coloring. Okay, one thing if you don't know anything about graphs is that it doesn't matter what form it takes. It matters exactly how many vertices there are and what are the edges connecting them. What I mean by that is let's create this sort of graph. It will be the same as this one. You can think of it if you just took strings and connected them with some sort of dots, and then you can just manipulate the graph. So here I would take this one dot, or let's say bead, and I would put it on the other side. I would put this one on the other side, and it would create this graph, and they are the same. So that's why I drew this one specifically in this way. Of course, these ones can also be drawn like this, in this form. Okay, and we have a decision problem, which we'll be talking about, which is for a given graph G, we want to find whether there exists a cut of size at least k. So in this version, we don't care about the maximum number. We just want to find one that is at least k. This problem is hard. It's NP-complete, which is very hard class of algorithms where usually the solutions are exponential and it's impossible to bring them to polynomial complexity. So there are 2 to the n possible colorings. Think about why. Because we have 2 colors, right? And n vertices. And so the brute force would check each of these cases, right? We just check each possible coloring. But here, that would be very, very difficult and it would take a lot of time. But by using Grover's algorithm in an appropriate way, we can bring it down to 0.8 times 1.414 to the nth, which is much better. Now let's say something more about a different type of graphs. So you saw how I drew this kind of graph. Let's draw one again. But here let's not worry that much about the colors. We can just name this as A and B. There will be some edges in between them. So a graph is bipartite if we can set it into 2 groups, A and B, just like I did, but we don't have any edges in between them. So inside the group, we have no edges. Like if we have 1, 2, 3, there cannot be any edge. 1, 2, 2, 3, 1, 3. And then it's bipartite. In a simpler case, say something like this, this would not be bipartite with A and B here. All right, so this is an example. And we see that the vertex 0 and 1, 2 and 3 could form such a set. So here we would have to draw it like 1, 0, 3, 2, and then 1, 3, 3, 0, 0, 2. Name it A and B, and it's bipartite. But here, that's impossible, because in this case, there is also an edge between 0 and 1. So this is a graph that is not bipartite. So they have a very specific property, which is you can always color them with two colors. Why? We just color each set, one set with one color, and the other set with the other color. And this will be useful in solving the math cut problem. Now, we want to check bipartiteness, and we can check it by finding whether a two coloring exists. And we have a specific idea, and this is important. So we want to represent our graph in a specific way. So n vertices, which will mean n qubits. And so the ith qubit will encode the color of the ith vertex in this way, where 0 means red color and 1 means blue color. We have our first task, and we want to implement this idea. So we are given a graph that is colored, and we want to represent it as a quantum circuit. So we have our inputs, and we have our registers. And what you just want to do is exactly implement these rules. So we'll have 5 minutes for that. Also, since this is a new topic, if there are any questions, please don't hesitate to ask, even if they're concern the basics of graphs, for example. I will gladly explain. All right, let's code the solution. We have our register. So first of all, what we'll do is we want to color. So let's remember what it was. So 0 is red color and 1 is blue color. So that means that what qubit 1 and qubit 2 need to be in state 1. And similarly, we're doing the same thing for qubit 2. And this is all we have to do. Okay, what do we have? We have 4 qubits, 0, 1, 2, and 3, just as in the graph. We are not doing anything to qubit 0 and 3, because by default they'll be in state 0. And on qubit 1 and 2, we're putting the NOT gates so that it will be in the color blue, so state 1. And let's check it. Qubit 1 is red, qubit 0 is red, qubit 1 is blue, qubit 2 is blue, and qubit 3 is red. And that's exactly what we're supposed to get. Let's switch. And now we'll say something about edge check. So we want to implement a protocol which will check whether an edge has endpoints with different colors. So essentially that's the beginning of our oracle. So for each edge, we'll use a different qubit. So remember that for vertices we're using qubits, and for edges we'll also be using qubits. And there we'll store a Boolean value, and the Boolean value will be coded in a quantum state, so state 1 or state 0. So if it's 1, the edge connects vertices with different color, and 0 if it doesn't. And for that, we'll use the XOR function. So XOR x and y will be equal to 1 if x is not y, and 0 if x is equal to y. So x and y are the colors of vertices, and the result is the Boolean value. So we can implement it using the CNOT gates. Here I don't have a proper solution, so let's switch. So let's see what we're doing here. We're using CNOT. We're using CNOT, where 0 is the control and 2 is the target, and then 1 is the control and 2 is the target. And our 0 qubit is x, 1 is y, and 2 is the result. So z is the third qubit. And let's see if this circuit is correct per our rules. So first vertex is set to 0 and second is set to 0. And so edge connects the same colors. So first and second, it would connect the same colors if there was an edge there. Now, first vertex is 0 and second vertex is 0 as well. So it connects, right, the same qubit with the same qubit, it will connect always with the same color. Here we have 0 and 1. And so it connects different colors, 0 and 1. And let's just go through this one. First vertex is 1, then it's 0, and of course it needs to be different colors. Since here we have 0, 1, and here we have 1, 0. All right. So this is the beginning of designing our oracle for tracking bipartiteness. And here, the Grover's algorithm at its heart, of course, is the oracle, which will mark an element. And the way of marking is already the thing that we did before. So we'll have an oracle that will be detecting an edge connecting two vertices that are colored with different colors. And then we'll use the Grover search to find the colorings if they exist. And it will mark the colorings. And then we'll use Grover's. Well, yes, to find the colorings, of course. So first we need to define an oracle. And as you can see, it will be maybe a more complicated endeavor than it would seem. So for now, we use separate qubits for each vertex and each edge. So each vertex is a qubit. Each edge is a qubit. This should already tell you that this will be a very limited example, since with graphs that are usually considered in computer science, they have a lot of edges, a lot of vertices, because the data isn't as simple. But here we just want to simplify it as much as we can so we can see how actually you can apply Grover's algorithm to a real problem. Well, so before the oracle will start the computation, so to decide whether the vertices are connected, like two different colored vertices are connected by an edge. So the all qubits representing the edges will be in the 0 state, and they should be in 0 state at the end, because we'll be doing iterations, right? And each iteration we want to start in a similar way. So here we want to have 0, and here we want to be in the same state that we were here in the beginning. this iteration. So now we can summarize the computation that we will be doing, or the Oracle will be doing after we code it. So first we'll be using the XOR operator to assign the appropriate Boolean value, which is this. And next, we'll use an additional qubit, and it will be set to 1 if the edge has the value of 1. And so here, let's say Oracle result, also qubit. And we can do it with the multi-control NOT operator, which will work in a way where we flip the value of the target if and only if all the controlled qubits will be in state 1. We have a second task. So for the given graph, we want to implement the first two steps that are described above. So we have the first 4 qubits are used for vertices. So we'll have 4 qubits, which will be vertices. Next 3 qubits will be used for edges. And the last one will be the output. And the last qubit should be in state 1 if the coloring of the vertices is correct, or in state 0 if it's incorrect. So we want to consider this graph, which we know is bipartite. So we already have the X gate on qubit 0 and 1. And now we want to implement these 2 steps of the algorithm. So for that also 5 minutes. We can start coding. Alright, so we have our color set first. And so we'll be checking specific edges here. So first, we'll check the 0, 2 edge. So 0, 2. We'll start in fourth qubit. And for that, we'll need to apply CNOTs on qubit 0 here. This is the control. And qubit 4 is the target. And then do a very similar way. But now with qubit 2 and 4 is the target. Remember that qubit 2, remember that qubit 4 is for storing our results, and then why it is the target. And then we're checking 0 and 2. So we need to do a very similar thing for the other edges. So first the 0, 3 edge, storing it here in the fifth qubit. Since we need all the results, we cannot right now use one qubit, although it is possible and a good optimization later, but for now let's simplify things as much as we can. So it's the 0, 3, so here it will be still 0. Then 3 is the control, and 5 is the target. Next, we'll check. So we have the 0, 2, we have 0, 3, last edge is 1, 3. And similarly, we'll store it in the sixth qubit. So the CNOT will look like 1 control, 6 target, and then 3 control, 6 target. And now we need to check that step might be easy to miss, but we need to check edge qubits. It might be a bit counterintuitive that we're using qubits for both edges and vertices, but that's something we just need to keep in mind. So here we want to do a multi-controlled CNOT, or rather CC0. No, this will be multi-controlled because we need to unpack a list and check all of our qubits from 4 to 7. So what we're doing is we're checking edge qubits, which is 4, 5, and 6. And those are the controls, and the target will be the qubit 7. That should be enough. All right, I didn't close. Here. Okay, parentheses, give me a second. Here, it's not closed. All right. So our measurement output is 1. Let's remember what that meant. So we use the output qubit and it will be set to 1 if each edge has the value of 1. So each edge connects to vertices of different colors. And this is a graph we talked about, which is bipartite. And so this makes sense. If you start at 2 and color it red, then it follows that you can color this one blue, red, and blue. And these are all the signals that we used. Okay. So we still have some work to do with regards to the oracle. So remember that the oracle will flip the sign of the amplitudes of the states, which will lead to 1 as the output, as this is how we define it. And we can do it easily with the z-gate, which we already did yesterday, if you remember. So when we have the sign 1, the sign is flipped. And if it's 0, is that it does not flip. Why? Because if we think about the state as alpha 0 plus beta 1, the z-gate would only change the amplitude near beta. So it would be alpha 0 minus beta 1. And we can do it by reversing every operator before the z-gate. And here with circ, we can use the method inverse. And we're doing this because then the oracle will be flipping the amplitude only of the signs that represent the proper coloring. Now, then our oracle is ready. So here, we want to try to apply the oracle and see how it works. So let's see, our oracle is here. And this is what we wrote. So we want to check 0 to edge, stored at the 4th qubit, 0 3 edge stored at the 5th qubit, and 1 3 edge and stored at the 6th qubit. Next, we're checking all the edge qubits. So that's our oracle that we wrote. Then we want to define oracle computation, where we'll apply the z-gate on the output qubit 7, and then we have to apply the inverse on the oracle. All right, and we want, so those are just functions first. And what we're actually doing first in the program is we're creating the circuit and we're putting all the states of the vertices in a superposition, and then we're performing the oracle computation. So here we'll have the results. So first of all, look at the last 4 qubits. All of them are set to 0. Let's remember. These are the edge checking ones as the output qubit. And they're all 0. Why? We talked about it in the notebook where we need to have it for the next iteration of Grover's algorithm. So this is a sort of post-processing we're doing after one iteration. All right, and the other thing we can notice is only the sign of 2 states, or rather, let's count 1 and 2 states was flipped. And why? Here we have 0, 0, 1, 1, and 4 zeros. The 4 zeros are what we discussed in a second before. And here, the vertices 0 and 1 are colored blue. Let's see. 0 and 2 are colored blue. 1, 3 are colored red. And what this means is those are our marked elements. And similarly, this is just a very similar way of coloring it. And we have our next task. So here we have different graphs. Alright, I think we'll skip task 4 when we come to it. You can do it on your own for practice. But let's do task 3. So we have this graph and we want to do 2 iterations of Grover's algorithm. And that's why setting the last qubits to 0 is very important. So there will be k equals to possible colorings. So we should apply it about 2 times. And here's the computation of the optimal number of iterations. And so we'll use 9 qubits. Why? Because we have 4 vertices, we have 4 edges, and we need 1 additional one for the output qubit. And remember, we have the diffusion operator, but we don't need to implement it here. We did talk about it yesterday. If you do not remember, you can refresh it by just checking out the last notebook. And we want to observe the outcome and the frequencies. I see some people need more time, so we'll have 2 more minutes. Alright, I'll start typing the solution slowly. First, we need to perform some oracle computation. Okay. So first, to perform the compilation, maybe let's start with the oracle. So with the oracle, we want to perform edge checks. And we don't have that, so we can write a function which will just simplify things. So here, we will be putting the C notes in exactly the same way that we've been doing. So A and B will be X and Y, and C is Z. Maybe not the happiest notation, but let's stay with it. And we'll do the same thing. And this is our function. So with the oracle, we can just write our edge checks. First, a check will be 0, 2, and we're computing it on qubit 4. Next, edge check will be for 0 and 3. So 0 and 3, there's an edge here. On qubit 5, we just need to do it for each edge that we have. So here, let's do 1 and 2. On qubit 6, edge check. Finally, 1, 3 on qubit 7. There's our oracle and oracle computation. Let's just put it here. Shouldn't matter, but just for readability's sake. Um, And here, first of all, we need to yield the oracle. And next, because let's see what we are doing here. The oracle computation looks like this, and this is what we are doing exactly. So first we'll be using the oracle, then we'll be using, definitely not here, but then we'll be using the Z gate on qubit 8, output qubit, and then we're doing the inverse oracle. And this should be all. Let's see. So first we're performing the edge checks. Then we're doing the oracle. Right, I forgot one thing, which is checking all the edge qubits. Target will be 8. Will be controlled by 4 to 7. And here we need to do it as a function. So we need to call it. Right, and now I wrote an extra Q here. This should do it. Let's see what we have. Let's remember that Grover's algorithm is a probabilistic algorithm, meaning we won't get results with 100% certainty. Well, in our case, this could happen, but it would be quite unlikely. Usually we'll take, because what we're doing is we're amplifying the amplitude that has the correct answer. Because of parameterized, that is true. That is true. And if you want to practice, you can do it for task 4. Absolutely matter. But yes, we have definitely see a drop off from 456 to 6. So with some epsilon that we're assuming of an error, we can say that these two are the correct examples, and we were computing it, and those are exactly the states that we got, if you notice here. Task 4, I will leave it for you to do as practice. And what did we do in this notebook? So we implemented Grover's search algorithm to find a two-coloring, which two-coloring is a very simplified problem. We'll try to do it in cases that are less trivial in the next notebooks. But of course, I think there are some things which might be counterintuitive here. All right. And yes, our algorithm takes O of 2 to the n and square root of it steps. But this exact problem can be solved in just n squared steps, meaning we made the algorithm as worse, but now we're just learning how it works. Then we'll learn how to write it for a problem where it will be much better than the classical solution. All right, and for now, we'll have a 10-minute break. See you soon. Welcome back, everyone. Now we'll deal with an interesting problem, which is at the same time very easy and very hard. Because all the time we're talking about the quantum model of computation, and we're comparing it to the classical one. And I think by now you've learned that sometimes the direct comparisons are hard to make because things are possible on a quantum computer, for example, superposition is not possible on a classic one, and vice versa. For example, directly, our gates that were not reversible, we needed to change them in a way that they would work quantumly. So now let's tackle a problem which seems very simple. Well, we have our model of computation, we have our gates, but an important thing is actually being able to add numbers. So we're going to be talking about a little bit of a simple quantum calculator. Here, I think it can be hard to see, so I might rewrite it quickly. So we have A, B, sigma, and C out. And we have this relationship. Then B is 0, 1, 0, 1. Alright. So that's us adding two bits, A and B. So if we're adding 0 and 0, we get 0, and here is our carry. Now we're adding 0 plus 1. And we're getting 1. I think this is actually reversed in terms of the carry. Mm, yes, that's a good idea. Well, then give me a second, I will change it to light mode. In this case, I'm afraid it won't work since the slides are anyway in dark mode. But I'll just quickly write it. It's alright. Well, then what we're getting is summing 0 and 1, we get 1. Summing 1 and 0, we also get 1. Summing 1 and 1, we get 1. Summing 1 and 1, we get 0 with the carry 1. Alright, I did write it in the other order. So this is the C out. This is the sigma. And let's not confuse it with the carry here. Alright. And we can see that the third column is the AND operator, and this is the XOR. So if we want to implement it in a quantum circuit, we only need 4 qubits and we'll simulate the half adder. So first of all we get double controlled knot on the third qubit, and then again controls on qubits 0 and 1. Alright, so this is the circuit. First, let's try to implement it. And for this we'll have 5 minutes. So until 8:45.
Sorry, but we don't hear you.
Oh, you didn't hear me. All right, sorry. Well, all right. What I was doing is I was showing the circuit, and yeah, thank you very much. I was showing the circuit, and we're just implementing the gates that are here. First of all, we have our NOT gate, which is controlled by qubit 0 and 1. And next, we have control NOT, a simple control NOT. Here you can note that if we have a multiple control NOT, it will show the gate X, but if we simply have a C NOT, it has a separate notation within the circuit. Hmm? And we're doing a very similar thing. On qubit 1, still control, still target will be 3. And that should be all. Okay, so we have all possibilities here. So this is showing which bits we're adding. And we can see the sum is 0, see how the carry is 0, with bit 0 and 1 and 0 is the same, where the sum is 1 and we're not carrying anything. And in this case, because it's modulo 2, we will have carry 1, sum 0. So this is what we wanted to see. Now, we are using a separate qubit, as you can see here, to find a solution. And so this is operation A plus B. If you think about programming where you can just say sum equals A plus B, we're using another variable, which does take up space, but when we're doing it on classical computing, usually it's not that big of a problem. So we can also implement addition in place. So B, it will be B equals A plus B, and we write it B plus equals A. And that also can be easily done with this circuit. So first of all, we're simply doing a double controlled C naught. 0, 1 are controls, 2 is the target, and then 1 is the target and 0 is the control. You can see the similarity here. So we still have this, and then we're just using another control here. And we can see that if we have Q0 and Q1 that are being added, then Q1 will have the sum bit and Q2 will have the carry, which is very convenient for us. And this is, of course, what we wanted to see, what we already analyzed there. All right, but we have the state Q2. And what if we have it in state 1? So we can check what happens. So here Q2 was 0, but if it's 1, we have 0, 0, 0, 0, 1, and it's 1 always, except for the time where we have two ones and it is 0. So when Q1 and Q2 and Q3 are in state 1, then we cannot use it exactly, but we can use the same circuit to add a single bit if what this case doesn't apply. Now counting. So we know how to add numbers now, which will be very useful in final notebook. And now we want to count numbers. So we have some n bits, and we want to see how many of the bits are set to 1. So it's some zeros and ones, we're counting the ones. And now we know how to add the two numbers. And now we will see the procedure for counting. So by adding multiple bits, we'll store the output in qubits 2, 3, 2 and 3, and 2 will be the sum, 3 will be the carry. And we'll do this trick that we did here, which is in place addition. And first we will add the bit represented by Q2, the output, and then we add Q1 to the output as well. So you can think of these as A and the output as B. So what we'll do in the end is first of all we'll do sum, which will be sum plus Q0. So we can also write it sum plus equal Q0. And this is what we already implemented. That's exactly the same as here. Okay, and Q2 is in state 0, so we don't need to use the double control not. And after we do the first addition, we'll have to do sum equals sum plus Q1. So now we can have an option where we'll be adding 1 and 1. So for this, we'll have a bit of a more complicated input, since first we want to control flip the output if 0 and 2 are 1s, or if 1 and 2 are 1s. But before that, we need to check whether 2 is 1. Alright, here let's try different inputs. Alright, we have input 0, 0, 0, 1, 1, 0, and 1, 1. And the sum is supposed to equal to 0. And it's 0. The sum should be equal to 1, and it's 1, since we have 0, 1, 1. And only in this case, see, we have the carry. And the sum is 0. So it's exactly as in the tables that we've been seeing before. So we have another task, and we want to implement this procedure. But this time we'll add 3 bits. And the sum will be stored in qubits 3 and 4. Okay, and first we'll add the first 2 bits. So we can have a situation where Q3 will store the 0 and Q4 stores the 1. And so the sum will be 2. Okay. So we can have 5 minutes for that. All right, we can go to implement our algorithm. And here I wanted to just to note that in my opinion, it is difficult to see how this translates to what we're trying to do. And here, if I had, let's say, if this was the last notebook, I would write it all out, but I do not have time, unfortunately. Here, what you can do is just write, those are the inputs, the sum and the carry. Choose some inputs for 0, 1, for example, 0, 1, and just see what happens. And if you put in a couple of inputs, you'll see what each C note is responsible for. So that's the way you can do it. Now let's implement the task. Here we have just the initialization. First we use the double C note where Q0, Q3 will be the controls and Q4 is the target. Next, and let's say, well, first plus qubit 0. And the next step of adding the 0th qubit will be adding a regular C note. But here it has to be 0, of course. And the next one will be the third one. Okay. So that's the first thing we're doing. It will not work, of course. This is just the first step. So as we can see, only the sum is not enough because we haven't added qubit 1 and qubit 2 yet. Here we can just copy this part. And here we have qubit 1. 3, 4 will leaving to be the same. And here we just have 1. You could similarly just make a function to make it a bit nicer. But let's just do it the easy way for now. That's the last thing we need to do. And here, of course, the only thing we're changing is we're changing it to qubit 2 since this is what we want to add. And let's see, all the results are correct. So here, for adding one number, only one double control note and a C note suffices, which is very good in terms of, let's say, space complexity of the gates. Next, we just want to see it all over again, but not on an example, but in general. So we have an input qubit A0 and an output qubit B0, and they are set to 0 initially. Afterwards, we have B0, which will be B0 plus A0. So what can happen here? Well, they were initialized B0 is initialized as 0. A0 can be 0 or 1, so B0 can be at most 1. And this is why we are using a simple C note. So this is simple enough, but we want to add more numbers. So if we want to add a 1, say, to the summation, B0 will be able to be 0 or 1. Because if we have two ones, then the modulo 2 will work and we'll get 0. If we get 0, we'll already have 1, so it can be 1 as well. So yes, we can have the overflows, and this is what we check when we have the double controlled NOT. So we're checking it for the overflow. So A1 and B0 are the control, and B1 is the target qubit. Okay, and now we can add A2 in a similar way. So if A2 is 1, the sum is 1. And in the similar way, we just have the overflow. So this is how our circuit will look in the end. Now we want to add one more qubit. So if A3 will be equal to 1, and both B0 and B1 are equal to 1, so the current sum will be equal to 3, then we'll have to sum to 4, and we'll need another bit. And so then we need to check all A3, B0, B1, whether they are 1 or not, and apply the NOT gate. So I know this is a bit tedious, but just understanding the concept will help us and will allow us to use it in the final notebook. So we can check the following circuit, and that implements the summation. Alright, so that just generates the input that we want here. And that's what we're doing, exactly what I just described. We're implementing here, so the C note first, because it can only be 0, 1, then double C note, and normal C note, and adding the Q3. So it does get progressively complicated as we add more qubits. And it will be just similar. You should be able to see the pattern of what we're doing if you write out the numbers. So just try to sum other bits that can have 0 and 1 and think about what the output can be and whether we will have an overflow or not. So when we add A5, A6, and A7, the sum can be at most 7. And so then we use 3 bits. And this will just keep going on when we add new bits. So the number of bits, if we want to know how many there are needed, when we have the 2 to the ith bit, and it will be included in the summation, then we need another multi-control NOT gate so that we check the overflow. Next, we'll see task 3. And I think we'll skip this one, since this is just addition in a very similar way. Now I can see how we can check the number. So we have two qubits, Q0 and Q1, which will store an integer. And we want to see whether this integer is equal to 3. So now Q2 is the output qubit, and it will be initialized in state 0. Then we'll apply the NOT gate on Q2, but only if Q0 and Q1 both are in state 1. So this will implement this idea. So remember that we're working about in binary numbers and the output will be an integer. And so we have the binary number B1, B0, and it will be represented in the circuit so that B1 corresponds to Q1 and B0 corresponds to Q0. All right. Okay, so that's why we're putting the state in state 1 first and putting the double control node on X. And here the number is indeed equal to 3. So here the binary representation, if it contains only 1, then we just need a multi-control node. But if we have 3 qubits, and we want to check whether it's 5, it will get a little bit more complicated. And so here we have a few conditions which will make our qubit flipped. So first of all, if the first qubit is in state 1, second is in state 0, and the third is in state 1. And so here again, we're designing the circuit so that we're looking at these situations and then seeing what has to happen so that the qubit is flipped. And then using a multi-control node, maybe an X gate, to implement this idea. So this is called pre and post processing. And we're doing it for the middle qubit. So basically, if we have a situation where, okay, we have this problem and I have the algorithm, but we need all the qubits in a specific configuration with specific states first. And that's we're doing pre and post processing. And pre and post processing can be either classical or quantum. So for example, classical could be counting the numbers of ones and zeros. And then based on the output, we can just either do another, let's say, iteration of an algorithm or not. And the quantum is just like, for example, using the NOT gate to set the state. And I think this is a more interesting task, so this is what we'll do. And we want to check whether the first 3 qubits will store the binary representation of number 5. And number 3 will be our output qubit. So we'll have 5 minutes for that. See you then. I think we can go and implement our task. So first of all, we are setting the qubits to number 5 because that's what we want to check. Next, if you want to set qubits to 3, you can, we'll try it later. But first we need to write our solution. So what we're doing first is we're doing the NOT gate on qubit 1, and then we'll be doing the multi-control to check for the carry. And finally, we'll do the same thing. Since usually in quantum algorithms, when we're changing something to another state, for example by get not and Hadamard, we'll usually be changing it back. So let's see. Okay, so the number is equal to 5, so our circuit is correct. And yes, we need to recover the qubits. And we were recovering by just putting the NOT gate at the end. And let's check if it works if our qubits are not equal to 5. It's not equal to 5. Very well. Now, sometimes we just want an inequality so that a number is smaller than something. So for example, we have two qubits, Q0 and Q1, and it's storing an integer. And we want to check whether this integer is greater or equal to 2. So we need to think, if you have a problem like that, usually we want to rephrase it in a language that's better for us. What does it mean that the integer will be greater than or equal to 2? You can think about the first bit and the second bit, what they would have to be. So we just want to check whether the value of the two qubits is 2 or 3. So let's note that 2 it will be 1, 0. So first of all, we could say, for example, let's check whether the first number is 1, and that should solve it, since we just want 2 or 3. And we don't want our state to be lower than that, so we don't want the state to be 0, 1 or 0, 0. And so the output qubit should be flipped if the qubit Q1 is in state 1. You might have in the quizzes, I didn't check these ones yet, but you might have questions like these. And here, the way I told you to solve it is, I would say, universal for these quizzes themselves, where you just want to notice some little thing. And for that, we want to rephrase the question in terms that we understand. So for example, here just writing out the possibilities and noticing the pattern. And so the only thing that we need is a single CNOT gate. And so we have measured input 4 and is greater than equal to 4. Oh, well, wait. That's we're supposed to do this here. Okay. So here it's not greater than 2, it's number 2 is greater or equal to 2, 1 is not, and 3 is. So all is working as we wanted. So we have to check one number at a time with a classical computer. And here we're finally getting to the part where we're not implementing something that is very easy on classical computers in a more complicated way. But what we're seeing is we can use superposition of states to check multiple numbers at the same time. So what we will be doing is creating a superposition of all integers that are possible, and they will be represented by the input qubits. And we'll use Hadamard gates, of course, to create the superposition, and then we'll be using the method that we just presented. So now we'll have a circuit with 4 qubits, where the first 3 hold an integer, and the last qubit is the output that will return the decision of whether the input is greater than or equal to 4 or not. So we can see whether it works or not. A couple of times. It does work indeed. Now and finally task 5. So let's see. I think this task is also okay. If someone wants to do this task, then please let me know on chat. Otherwise, we'll skip it because of time constraints. But remember, if I'm skipping something or you feel like I'm going over something too fast, you can either ask me now or you can write to me after the lecture, and I try to answer as fast as possible. Alright, then we can skip this task. Okay, we can skip this task and we'll have a 10-minute break until 10:27. All right, I think I'm
We cannot hear you.
all right, thank you. Well, it's time to go to the final notebook, which will be the culmination of our efforts, and we will be able to implement Grover's algorithm for the max cut problem. And just as we ended our last notebook, we will try to use the quantum property of superposition to speed up the solution for the max cut problem. And the superposition will be applied to the qubits, which represent each vertex. And we already did implement Grover's diffusion algorithm. And we need to have a specific oracle which will mark the colorings where we have exactly k edges whose endpoints are using different colors. Okay, and now we have the algorithm where this is an algorithm for the oracle. First of all, we need to implement the edges and the edge checking for each edge. So that's the checking whether the endpoints have different colors. Next, we're using what we learned in the previous notebook, which is the sum the outputs of the edge checking step. Next, we need to see the sum and compare to k. It can be equal to k or greater than k. And then we'll save the flag on the auxiliary qubit. And finally, we'll apply the Z gate to the auxiliary qubit. This will be our oracle. And the oracle works for one version of the problem, and it checks whether there exists a coloring such that there are at least k edges whose endpoints are using different colors. So this is the formulation of the problem we'll be solving. So now k will be a 3-digit number. B2, B1, B0. So now first thing we need to do is to check whether there will be a coloring where B2 will be equal to 1. Since we want the number to be greater, right? So we have B2, B1, B0. So first we're checking whether we have 1. So if it is, we're checking if there's a coloring such that there is B2 is 1 and B1 is 1. And if not, we want to check whether there's a coloring with 1 here, B2 equals 0, B1 equal 1. Although, no, it will be B2 equal 0, B1 equal 1. And this way we'll be doing the binary search over binary representation. So we can first consider the graph. And here you can also already see something specific about how we implement the oracle. And that is, since we need to implement edge checking, we'll have a different oracle for each graph, which might be a problem if we're trying to have a solution in a practical sense. But in that case, you could think of whether it is possible to automate it or not. So we have a very simple graph here. And we want to find whether there is a coloring such that two edges connect the vertices with a different color. We can see that obviously there is such a coloring. And so we need to verify whether the number b1 be 0 and b1 will be set to 0. Okay. So the qubits. First of all, we'll use 3 qubits for vertices since we have 3 vertices. We have 2 edges, so next qubits are the edge qubits. Next, we need, since we have 2 edges, we'll need 2 qubits for storing the sum, and it will be the qubit 5 and qubit 6. And finally, the output qubit, number 7. And it will store the flag that will show us whether B1 is 1 or not. And then that's why we have to apply the Z gate on that qubit. So in the simple version, we can look through the code for the Grover algorithm that we're implementing. First of all, let's see the oracle. Oh no, first let's see oracle computation. Okay. As previously, first thing we need to do is edge checking, where we're essentially just putting C nodes on where, so first of all, Z, we're checking the 0th qubit and the 3rd qubit is the target. The first one, where we're also storing it in qubit 3. And then the first one again. And the second. So that's just edge checking. Then we need to do adding, which we were doing in a previous notebook. And what we need here is the control NOT gate. Here we'll be using the 5th qubit. And finally, to store the 4th qubit, since we are adding another number, we will need the double controlled NOT gate. And this is what we're doing. And obviously, the control NOT gate at the end as well. So, and finally, in our oracle, we need to check whether B1 is 1, and then store the result in our auxiliary qubit. So number 7. And with the oracle, it has the same structure as before, meaning we're computing the oracle, putting in the Z gate on qubit 7, so the auxiliary qubit, and finally putting in the inverse, since it will be only one iteration of Grover's algorithm. Next, we're implementing the diffusion that we were also doing yesterday. So first of all, we're putting everything in a superposition with the Hadamard gate. Next, using the NOT gate, since we're implementing the diffusion operator as minus D, not D. Then we're using the Z gate so that we can flip the state and obtain the result. So here it will be double controlled Z naught Z gate, which will be controlled by qubit 0 and 1, and the target will be 2. And next we need to get back to our previous states, meaning first of all we need to do the X gate and the Hadamard gate so that it's nice and symmetrical. And finally, the Grover's algorithm. First of all, we're creating the registers. We're putting everything in an equal superposition with Hadamard. And, well, not everything, only the vertex qubits. And then we're append the circuit with the oracle and the diffusion. Okay, and we're appending the measurement. And so we have our results. Next, we're doing the trials, the samples. We'll print a random guess probability. And then we want a histogram of the result, which we've seen the function bitstring already. We're using counts. And finally, we'll print the probability of observing a certain state. So for example, here we see the random guess probability being 0.125. And now the probability of observing 010 will be about half, and probability of observing 101 will be also about half. And those are the two colorings that we can have. Remember that we can denote, I don't really remember, it's arbitrary what we have chosen, but if, for example, red one was 0 and blue one was 1, the only two possible colorings will be blue, blue, or red, blue, red. And this is exactly what we have gotten here. And now we'll have a couple of tasks where you will be able to implement the Grover's algorithm for different, maybe more complicated graphs. And these I would like to do all of them. So first we'll do the first task. And we have this graph that we've already seen. And we can check whether there's a coloring in which there are exactly 4 edges. And here you can think about what we're talking about bipartite graphs and think about whether this one is such a graph. And next, I'll give 5 minutes, but if you're not done by this time or a bit earlier you're seeing that you don't have enough time, then please just put not the full moon emoji or the timer so that I will know to extend the time. I think I'll wait until the timer and the crescent moon will change into full moons. And I'll wait at most 4 minutes, I think. That's quite okay. It's a complicated algorithm because it's the culminating one, so please take your time. Alright, since I think it is important that you have enough time to complete this task, we can wait some more time. But please, if you do complete the task, do change the emote to the full moon. Okay, I see people finished. In that case, we can write the code. Okay, so first of all, we need the vertices are 0 to 3. Then for edge checking, we'll take 4 to 7. Then for the addition, we'll take 4 to 10. And 11, it needs to be the auxiliary qubit. You can see it from the previous examples, or you will see it as we will be writing the code. So let's write, we had the edge check. Let's see if I have it here. No, I can write it quickly. There will be a bit of writing here. So now we're checking A with C. And we'll be checking B with C. Next, the oracle computation. When we will need to yield an edge check. Okay, let's see the edges. First of all, 0 to 2. 4. Next edge, let's take 0, 3. And we'll start in qubit 5. Next, we'll have to check 1 with 2. And we'll start in qubit 6. And we need to check finally 1 with 3. And we're storing it in qubit 7. But that's not all. There will be more, since next thing we need to do is we need to add the outputs of the edge stacking that we did. So first, let's do a CNOT. Of qubit 4 and qubit 8 will be going exactly the same as we're going in the adding notebook. Next. So this is the easy one because our output can either be 0 or 1. Now we'll have to introduce the double control nodes. And 8. And finally, target being qubit 9. And a simple CNOT later with qubit 5 in the control and qubit 8 being the target. Okay. And next we'll be doing the same thing. For now we don't need to introduce another controlled node. So here it will be 6 and 8 with qubit 9 here. And similarly we need to change 5 to 6 here. And now since we're going over the 2 to the ith, here we will need to introduce the control node. So it will be a NOT gate with qubit 10 as the target. And it will be controlled by, let's go to the list. So all the qubits from 8 to 10, including 10. And in here, we don't need to undo the NOT gates. It's necessary. Now we're doing our standard oracle, which will be oracle computation. Next, the Z gate. And this will, of course, going to yield. And this will be the 11th qubit. And we're going to do the inverse. And finally, Grover diffusion. So first of all, introducing the equal superposition. Zero to 4. Next, the NOT gates. On the same qubits. Multi-controlled C gate. So the qubit 3 will be target here, and we'll control it. All qubits until 3. And then we're doing the same thing so that it's symmetrical. And so you undo everything until the next iteration. And finally, the Grover algorithm proper is implemented. I probably forgot some parentheses somewhere. Let's check. Let's see, where is it? Circuit Pen Oracle. Let me check. Here I'm missing something. The actual qubits. But that's not the main problem. I check 0 to 4. And that should be okay. Six, 8. I think I forgot something here. So first we have the multi-controlled X, but I forgot to add the double controlled X gate with qubit 7, qubit 8, qubit 9. And next, a simple control NOT gate with qubit 7 and qubit 8. And finally, that's what we did, and we forgot another part, which is after all this, we actually need to check whether the number is equal to 4 or not. So let's put a note on X here, another not gate. And finally, a multi-control node. And it will be controlled by a list of qubits from 8 to 11. I think I still see a problem. So we have the X here controlled by here. It will just be 7 to 10. 8, 9, 11. Let's see. So this here is the problem. Here's one problem and another matched here. See, and here okay, fine. It's sometimes hard when the code is so similar. But let's see. Let's see again. So we have another two possibilities which have a significantly higher probability of observing them than all the other ones. And they're about half. So 1, 1, 0, 0, 1, 1, 0, 0. And here it works because the 1 and 1, the same color, they are not connected. And similarly, these two are not connected. And the only ones that will be connected will be these ones. And this means it's a bipartite graph, and that will be optimal. And here, that you will see usually two options, or at least even options, since we can color it with blue and red, or with red and blue in a similar way. Okay, this will be again left as an exercise before the assignment, since I think it might be good to practice a little bit, since that might be the hardest part of the assignments. And let's talk about a little bit what we did and what the significance of it is. We had a problem, which is a real problem and one encountered quite commonly in normal, like classical computer science, which is the max cut problem for graphs. And here it's something a little bit more complicated. Before you could give examples of the Grover's algorithm working on a database where we have just strictly a function, here we have something different. So first step is, if we have our problem, we would like to see whether it is possible to implement it in a way where we can apply an oracle-based algorithm, in this case, Grover's search algorithm. So for that, we need to find something that we'll define as a function that will just tell us whether some property is true or not. And this property needs to be found in a fairly clever way. Just like here, we're checking whether a certain edge has two vertices of different colors. And that was the first step. Then we need to see the oracle. Since Grover's algorithm is the same in structure, but one, depending on the number of qubits, it will have a different number of iterations. And additionally, the oracle is different for each problem. And here, the most important thing is we want to see whether it is possible to implement such an oracle at all. In our case, fortunately, it was, but we noticed that you need to have a different oracle for each problem. And here, I think it would be possible to automate it, as in write an algorithm that for each graph it would write an oracle. In other problems, it might not be so simple, and in that case, we cannot automate it, then Grover's algorithm might not be a good idea. And next is the little things. For example, we needed to learn how to add numbers in a quantum way to be able to complete the oracle. And very often you'll encounter such small problems, seemingly small problems, which might be harder than they seem. Because classically they would be easy to solve, in a quantum way they are not. And finally, we have our working algorithm, which we can apply to different things. And here, if you're looking at some paper, let's say, and you see a quantum algorithm, very often it will be very complicated or seem very complicated, since you will see just a lot of C nodes, for example. Very often you see C nodes and control nodes, Hadamards, Z gates. You'll probably recognize the gates, but they will seem like they're in just there randomly. And for that, you need to just see the block structure of the algorithm first of all. So just like we have the oracle, we have the diffusion, we have each iteration. That's the first thing. We can try to see what the most important thing is, like the heart of the algorithm. For example, here it's the oracle. And then try to understand the, again, quote unquote, little things, just like the adding of numbers in a quantum way. Alright. So, yes, with the exact way we implemented this, there are small problems, since, or rather, places to optimize the algorithm, since we could reuse a single qubit for all the edges. And the circuit would be longer, but we could save qubits. Usually, qubits are much more costly than the gates. And next, we were given the number of iterations, but usually we'll just calculate it. And there is a quantum algorithm. It's very handy. That's called the quantum counting algorithm, which can determine the number of solutions. Are there any questions? Okay, not for the moment. So if you have any questions, since this is the last day of the workshop, please ask them on Discord or write directly to me. I am glad to answer them whenever I find the time. And I hope you enjoyed the material that was presented in this workshop. And again, any questions you have, then please ask them. In terms of the lecture notes from yesterday and today, since I am abroad, I won't be able to give you them today. I'll give them to you Sunday evening. And then you have another week for completing the assignments if you so wish. Later, you'll receive the information that you qualified for the certificate. You'll have to wait some time until the certificates are ready, and then you'll receive them. Alright, in this case, if there are no more questions, then thank you very much everyone for coming, both the people that are here right now and the people that are watching the recording. It was a pleasure, and I hope maybe we can meet some other workshop.
Thank you, Alex, also for conducting the workshop. That was great, as always. And
Thank you very much.
I also hope that our participants enjoy it. And yeah, so as Alex said, you will have time until Friday to submit the homeworks, and then it may take a few weeks to generate and send you the certificates if everything is fine. And we'll probably announce it tomorrow or on Sunday, but next week, starting from next Saturday, we'll have the QPoland Global Quantum Hackathon. So it will be Quantum Computing Hackathon, in which you can participate and already use the skills that you've learned during this workshop and also during the previous QBronze workshop if you participated. But there will be a separate announcement, but you can already save the date because it will start on 19th of October and it will last until October 27th. So there will be 8 days of the hackathon. So stay tuned. We'll later also send you a feedback form to ask for your feedback. And yeah, if you have any suggestions on how to improve, because this is the second QNickel workshop that we've organized as QPoland. And I think that this is the first workshop in which we have the assignments in the homeworks. Last year we had only the quizzes, and this is relatively new educational material. So we are also looking for your feedback, and we'll do our best to improve these materials for the future. There are also some links. Yes, there are also some links that we've shared. If you want to stay up to date, you can join our groups on social media or follow our profiles. Stay up to date and be notified about the next events, next workshops, the hackathons, contests, conferences, meetups that we organize. You can also subscribe to our monthly newsletter, QPoland newsletter. That's all from me. So thanks once again. And Alex, you wanted to say something? Yes.
Yes. There's a question whether there is sub-circuit design in Circ. There is. I think you can use it with the circuit operation, so circ.circuit operation function. And yes, we didn't delve that much into Circ, just like practical things so that we can implement basic algorithms. And thank you very much, everyone. Again, thank you for the question and for being here.
Thank you very much for everything.
Thank you.
You're welcome. Good luck with the homeworks and have a good weekend.
Thank you.
Thank you. Goodbye.
Thank you.
Thank you very much.
Thank you.
Goodbye.
Thanks a lot.
Bye.
Bye.
Very much. Bye.